Now with arithmetic sequence, we go from arithmetic sequences to arithmetic series, and it leads into probably one of my favorite little stories about mathematicians. We talk about Carl Friedrich. Probably spelling that wrong, but Carl Friedrich Gauss. Now, there's a nice little story about him, a little bit of history. Traditionally, the only people that were able to afford uh, for their kids to go to any kind of secondary or any kind of actual schooling were people that had money. Now, I have to actually go back and check to see whether Gauss actually came from a wealthy family. Uh, Obviously, it's very different now because we want everyone to actually have an education, not just the people that are in the higher brackets of earning. But Carl Friedrich Gauss, the way that the story is, he was somewhere between the ages of 7 to 10. And the story that, or the version I heard is he was being a little, how to say it, not a very good, well-behaved student. And the reason he wasn't a very well-behaved student is because he actually knew what he was doing. So while his classmates were doing something a little more menial, his teacher just asked, okay, what's the sum of the numbers from 1 to 100? So on and so forth. Thinking that that might take him a little bit just to get him out of their hair, whether male or female. I don't know exactly whether it was male or female. And he, but again, the story that or the version that I heard is within a few seconds, he immediately came up to the answer, 5,050. Teacher was like, what the heck? Like, how were you able to do that fast? Because 5,050 is the correct answer. Now, the exact way that he did it is actually developing into a few bits of understanding. For example, if you take all the numbers from 1 to 100 and you lay them out, that would be the exact same thing as starting at 100 and going backwards from 100 down to 1. Oh, that's pretty fancy because there's something kind of interesting about lining these numbers up the way they are. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. And it continues on forever. Or until, sorry, not forever, but continues to the end. But if you take 101, that would be 100 of them. So that'd be 10,100. We only need to know from numbers from 1 to 100. We don't need to know from 1 to 100 and then 100 down to 1. So you divide it by 2, and you get right back to 5,050. So what he had been able to derive is actually these two formulas between the ages of 7 and 10. Again, don't know exactly when it was, but this is kind of just one of those fancy stories. Obviously, don't know the full legitimacy of it, but it's still one that's fun to talk about. In high school, don't necessarily talk about a huge amount of Greek alphabet, but overall, the formula comes from here. Starting at 1, and our n being 1, we're finding the sum of all this. So this fancy letter, it means sum. So we're going to add up some numbers. Now this is actually a capital sigma. And so this is a capital sigma. The lowercase sigma is actually this. So this is just kind of a little tidbit that I like adding in, just because understanding a little bit of the Greek alphabet doesn't hurt too much. So when we are finding the sum of an arithmetic sequence, because we could have just listed the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 100. That would be our sequence. But when we find out the sum, that's when it becomes an arithmetic series. So a sequence, just back to our section 1, is just listing the numbers, whereas a series is actually adding them together. And we have two formulas that actually talk about that. There's this Sn equals n bracket 2 times t1 plus n minus 1 times d all over 2, or Sn equals n t1 plus tn over 2. The good news is almost all of these variables are the exact same as, or sorry, are ones that we've already learned. They are the exact same as the ones that we had done in the first section. N is still the term number. It could be the 5th, it could be the 7th, it could be the 23rd, whatever it is. So those n's are still the same. T1 is still the first term. So that's still good. D is still the difference. Tn is still our general term, or nth term, whichever term we're looking for. The only additional news that we have in this section is this Sn. And those Sn's mean the exact same thing. All it means is the sum of n terms. So it could be the sum of the first 100 terms in this. So I guess it comes down to which formula do you use? And the answer, it depends on what you have. If you have the difference of term 1 and you have however many terms there are, you're going to use this one. If you have how many terms there are, you have the first term, and you have whatever the general term is. So for example, the 100th term or the 17th term, you can find out a sum of those 17 terms. So let's go through an example here. 2 subtract 3, subtract 8, subtract 13, subtract 18, subtract 23. This is still a series because it's 2, add a negative 3, add a negative 8, add a negative 13, add a negative 18, add a negative 23. We'll notice that each of these numbers, really quickly, well, actually, let's do that as a quick calculation. Let's find out what that difference is. Negative 3 subtract 2 is negative 5. Negative 8 subtracting negative 3 is negative 5. Negative 23 subtracting negative 18. Yeah, our difference here is negative 5. We are going down by 5 every single time, and we're just going to add them all together. So to answer, which formula do you use? Do we have how many terms there are in here? Absolutely, we can actually just quickly count them in this case. 1, 2, 3, 4, 5, 6. So our n is 6. So the sum of 6 terms, of these 6 terms, with this criteria. So our n is 6. Our term 1, in this case, is 2. Add 6 is the n, subtract 1. Our difference is negative 5. All over 2. Not 2a this time. Sorry, a little bit fun. Anyways, we're going to evaluate what this is. So please use your calculator. Be smart about it. Don't give yourself that much of a headache. 2 times 2 is 4. 5 times -5 is -25. So 4 add -25 is -21. Make sure I'm putting that in my calculator. Doing that right. 6 times -21 divided by 2 should be -63. So that's one way of doing it. Let's use the other equation though, because we also know all of our information here. We still know how many terms there are. There are 6. So the sum of these 6 terms, the formula is n times t1, which is 2, plus tn. Well, in this question is asking what is term 6? In term 6, it's -23 divided by 2, and it's still becomes 6 times -21 divided by 2, still -63. So no matter which equation you use, you still get the exact same answer. Now this formula, this one, might not be the easiest. Of course, we can absolutely count this one. This one's actually not too bad. We're just going to confirm, we're just going to do a little bit of math before we even get to it. If 4,000 is our first term, so that's nice. That's term 1. We can easily determine that our difference is 1,000, because we know that we're going up by 1,000. We don't know a few things. We don't know what n is. Now, if we count it, if 4,000 is term 1, 6,000 is term 3, oh, we keep on going. This should be about term 15, if I'm doing my math right. Let's go back to section 1 and just confirm that. Term 1 plus and subtract 1 times by d. We're trying to find out that 18,000 is term 15. So just by counting, we can find that out. We might not know that all the time. So we're going to manipulate the equation to confirm that n is 15. Hopefully it is. Hopefully I'm not saying the wrong number. And subtract 1, our difference is 1,000. So manipulating the equation, subtract the 4,000. $14,000 and subtract 1 times by 1,000 divided by 1,000. We get 14 equals n subtract 1. So by adding the 1, yeah, n equals 15. Sometimes we're going to have to mix our formulas in our questions in order to do our questions properly. In this one, we needed to confirm that our n was 15. It's not always going to be nice that we can count it up. Because what about if this was 7 and our next number or final answer was 1,236,000 and 7? Sorry, that was a really bad number, but we're not going to want to count all the time. So by using the formula, we can confirm that this sequence, this series, because we are adding them, has 15 terms. So then the sum of 15 terms, it doesn't matter which formula you use because we actually do have everything. This one is just shorter because we know how many terms there are. There are 15. Our term 1 is 4,000. In this one, this is no longer term 6 because that was the first question. This is what term 15 is. Term 15 is 18,000. That's 18,000 all over 2. Of course, I would expect that you'd be able to type this straight in, get the answer, but I'm just going to go one step at a time. This would be 22,000. So this would be 165,000. You might not think in this question that it's faster to do it this way, because we had to do a lot of work. We had to do a lot of explaining. Because you could have just typed 4,000 plus 5,000 plus 6,000, all on and on and on. And it could have probably gone to 165,000 a lot faster. But that's not the point. The point is, what about if these numbers are not easy to calculate? What about if we had 1 million numbers to do our addition with? Hopefully we won't have any questions like that. I think I usually cap out about 99 terms. But typing in 99 different numbers is going to take you a long time. It's going to actually overflow your calculator, and you're going to have to do probably multiple steps in order to add your numbers. This is always going to be faster. So one thing I just wanted to make a little extra, this is just a kind of a pay attention bit. These are the two formulas. There's this one, and there's this one. That's not S times N, that's a subscript N. M T1 plus Tn. Just to confirm that they are actually the same equation, because Sn equals Sn no matter what. I just want to point out one thing. Tn, the equation for Tn is back to section 1. That's T1 plus n subtract 1 times by d. So this entire bit right here is this. If you combine your like terms, T1 and T1 is 2 T1s. So I just wanted to kind of point out that, yes, these two equations are saying the exact same thing. They are equivalent. It's just going to be sometimes easier to use one rather than the other. The only reason I chose using the second equation for this one is because I didn't have to write a whole bunch of numbers. I could have. I would have still gone to 165,000. All right. Let's do some more examples. Male fireflies flash various patterns to signal location or to ward off predators. And different species also have different flash characteristics such as intensity, rate, and the shape of the flash. Meaning, like, it might grow, it might be really, really fast. They're an animal. They really typically it's dependent on temperature, but there's also different aspects. For example, to ward off predators. That's kind of one thing. Suppose under certain circumstances, a particular firefly flashes twice in the first minute, 4 times in the second minute, 6 times in the third minute, and so on. If this pattern continues, what is the number of flashes in the 30th minute? Well, using this, we're just looking for what is a pattern. Obviously, we can determine that really quickly, but let's use an equation. We want to know how many flashes. What is the number of flashes in the 30 minute? We don't need to know how many total numbers. That's actually B. In this question, we're going back to section 1. What is term 30? Or in the 30th minute, how many flashes would there be? The first minute, so T1, sorry, I'm just going to rewrite that equation. Tn is T1 plus n subtract 1 times by d. Our first term, in this case, is 2. N is 30. D is how much it's going up by. 2, 4, 6, then it'd be 8. So our difference is 2. 30 subtract 1 is 29. 29 times 2 is 58. You very likely would have been able to do this right in your head, but there would be 60 flashes. They go literally 1 per second. Using this, whatever circumstances this night was. We want to find out the total number of flashes in 30 minutes. And once again, I'm just going to prove that these two equations are saying the exact same thing. So the sum of all these flashes. So in the total number of flashes after those 30 minutes, so we're going to be taking the 2 plus the 4 plus the 6. So on and so forth until it is fully finished. So the sum of those 30 minutes, however many, those 30 times, we're going to find out how many flashes would be in total. So our n is 30. So that's going to be the same. 2 times our term 1. Our term 1 is twice. In other words, 2. 2 subtract 1. Our difference. Sorry, not 2. Sorry, that should be a 30. Sorry, I'm getting ahead of myself. That's our difference. 30. Difference is 2 all over 2. So 30. 4 plus 29 times 2 is 58. So 62. 30 times 62 divided by 2 is 930. So after half an hour, this particular firefly would have flashed with bioluminescence 930 times. So let's use the other equation to just say that, yeah, it's still going to be 930. So the sum of 30, term 1 is 2 plus Tn. In other words, what is term 30? Well, we actually calculated that up here. It's 60. So 30 times 62. Oh, that was terrible. 30 times 62 divided by 2 is the exact same formula as there, so there's no reason that it should be different. Unless you somehow type it into your calculator wrong, but it's still going to be 930. So you tell me, what is going to be easier? Typing 2 plus 4 plus 6 plus 8 plus 10 on and on to your calculator until you get all the way to add 60. You get to 930, and you would fill your calculator up the entire time, or are you going to use the formula? I hope that the answer is use the formula. Okay. So let's go over the last example. It's going to look very similar to the last one that we had done in our last section. Because it says the sum of the first 2 terms of an arithmetic series is 19. The sum of the first 4 terms is 50. What are the first 6 terms in series and the sum all the way to 20 terms? All right. So we know, again, we know a few things. We know that the sum of the first 2 terms is 19. We also know that the sum of the first 4 terms is 50. What we're going to do is we're going to plug everything that we can into here. We know that n is 2. Now I'm just going to change this to equal to saying sum of 2 is 19. Sum of 4 is 50. n in this case is 2. We don't know what term 1 is, though. But that's fine. We don't need to yet. N is still 2. And we don't even know what our difference is. We could have potentially used this one, but it's just going to, we know a little bit less in here. Actually, I've never done it this way. I might try and do this on my own just to see if it will work out relatively nicely. I'll try it another time. All that we're going to have to do here is we're going to have to do some manipulation to try and get some things by themselves. For example, the first thing that I can do is a 2 and a 2 actually completely cancel off, which means we'd have 2t1, 2 subtract 1 is just 1, d. So 19 actually equals 2 times term 1 plus our difference, which also kind of makes sense if you look in the grand scheme of things, but we'll talk about that after. Or we might not, I just might mention it as part of a class bit. Continuing on here, 4 will be the n on this one, times by 2t1 plus 4 subtract 1 d all over 2. I'm actually just going to quickly, I'm just going to lock this. I don't have anything underlined. So I don't. Oh, sorry. It's locked. So I don't lose things. Just going to rearrange this a little bit here. Just going to move it a little bit closer just so I can get all my work on relatively nicely. I can reduce a few things. For example, 4 and 2 gives me 2. So I'd have to have 50 equal to distributing a 2 into each of our terms here. I'm going to kind of step or combine a few steps here just for a little bit of space and time. 2 times 2t1 will be a 4t1. 4 subtract 1 is 3, so 2 times 3 is 6. What we are then going to do is we're going to combine these two equations. Well, in order to combine it, we will want to try and get one of our variables alone. In this case, it's this d. We want to get the d by itself because it is already by itself. All we'd have to do is subtract a 2t1. And our d value is completely alone, which means we can then take this and plug it in over here. So I'm going to make this purple here. D is d. So we're going to go and plug it in. 50 would equal 4t1 plus 6 times 19, subtract 2t1, and combine what we can. 50 would equal 4t1, distribute our 6 in, 6 by 19 is 114, 6 by negative 2 would be a negative 12. Now I'm going to subtract my 114 over. So we get a negative 64. 4t1 subtracting 12t1 will be a negative 8t1. And then we can divide both sides by a negative 8. So the first term would actually be 8. Negative 64 divided by negative 8 is 8. So we know what the first term is, but we don't know how much it has to go up by, which means we actually have to take 8 and plug it back into here to find out what our difference is. So the difference would equal 19, subtract 2 times by 8. 2 times 8 is 16. 19 subtract 16 is 3. So our first 6 terms, which the question is asking for, which is actually the first thing, our first 6 terms will be 8, 11, 14, 17, 20, and then 23. So to find the sum to 20 terms, we're going to have to use one of our formulas. And I'll actually change that into a black. Sum of the first 20 terms. Between the two formulas, this one and this one, we don't know what term 20 is. Absolutely, we could use our formula right here, this one, to find out what is term 20. But since we already have all of our information for this one, we're just going to use that one. So 20, 2 times term 1, which is 8 minus n, subtract 1, n is 20, times by our d, which is 3, all over 2. 16, subtracting 19 times 3. Oh, did I do something wrong? No, that's definitely not right. What did I do wrong? Two times t1, 20. Oh, it should be add, duh. Wow. Not subtract, sorry. 20 times 73 over 2. That'd be 730. So we just kept on going all the way up to 20 terms. We'd be at 720. Sorry, 730. Sorry. Alrighty. See you to have some fun.